Hi there. In a previous video we had shown how Max Planck had proposed that energy is not continuous, but it is composed of small packets or indivisible packets called quanta. And he had come about this from studying or trying to explain the black body radiation curves that were known at that time, and we remember that he proposed that energy is absorbed or emitted from a body in discrete packets. So rather than energy be continuous in nature, it has got a granular quantity, if you like. Now, another experiment that was difficult to explain at that time on the basis of the wave-like nature of energy was called the photoelectric effect. Now, the photoelectric effect, in very simple terms, can be described as follows. So, if you have some form of metal here, so here's your metal, and then you have some type of incoming electromagnetic radiation. And what was known that if the conditions are right, then you will have electrons will be emitted from this metal. And without getting into the detail on how these are measured, you can have some form of detection mechanism. So we have a detector over here, and again, without going into details, what you can do is you can measure the kinetic energy of these emitted electrons. So it was proposed at that time, before the advent of quantum theories, people thought that electromagnetic radiation had some wave-like nature, so you can imagine a wave coming in like that. This is your electromagnetic radiation. And if you consider energy as a wave, then what you would expect if you study how the kinetic energy of the electrons that are knocked off, how they vary, you would expect the energy of the electrons to vary directly with the intensity of the waveform of the energy. Now, under conditions in which the electrons were emitted, if you plotted the kinetic energy of the emitted electrons, and you plotted that as a function of the intensity of the incoming radiation, what you found was, you found a line like that, there was no variation in the kinetic energy of the electrons as a function of the intensity of the radiation. What was found, however, was that if you plotted the kinetic energy of the emitted electrons as a function of the frequency, which we call nu, of the incoming radiation, what you found was that as you increase nu, there was a certain value here before which there was no emitted electrons, and after that then the kinetic energy of the emitted electrons varied linearly with the frequency of the radiation. Now, this really cannot be explained satisfactorily in terms of a wave-like nature for the incoming energy. But what Einstein proposed was that this is evidence that in this case the energy is behaving not like a wave but like a particle. What he further proposed was that these particles correspond to what Planck was referring to as the quantums of energy. So he said that E is equal to h nu, and these are the quanta, if you like, particle-like nature of energy, and that these are behaving, the energy now in the photoelectric effect that we're watching up here is behaving just like a classical particle. So if we take out the wave-like nature here for our electromagnetic radiation, so if we draw this again, so here we have our incoming electromagnetic radiation, and what Einstein was saying was, instead of behaving like a wave, you should think of it as a stream of particles, and these particles correspond to this h nu. So now you can understand this like a classic particle. So you have a classic on the snooker table. So you have an incoming particle. It hits the electron. If it's got enough momentum to knock the electron out, the electron will move from its position. And if it's got more than enough energy to knock that electron out, then the extra energy will be transformed into the movement energy or the kinetic energy of the electrons. So this really, if you think about it, explains this curve down here quite nicely. So here you get kinetic energy, and what we said before was that you have some threshold frequency, which the energy must have before any electrons are emitted. And this corresponds exactly to the value of the energy needed to knock the electron out from its position. Again, going back to the snooker table analogy, the snooker ball is held on the table, and you will require a minimum momentum to just knock it from that position. So that will correspond to there, and then if you hit it with greater energy than needed here, then that extra energy will be transferred into the kinetic energy of either the billiard ball, or in this case of the electron. So what we call this threshold frequency here, we give it it's usually given a special name, and it's called nu sub 0. So this again is called the threshold frequency. And the corresponding threshold energy will be given by h nu 0. And that's often symbolized by the Greek capital letter phi. So what we can write, therefore, is we have our inputting photon energy. So let's put that in yellow. So our inputting photon energy, which is h nu. So what we can say that that's going to be equal to the threshold value of the energy. And then if there's any extra energy from knocking the electron out, that will be transformed into the kinetic energy of the emitted electron. So we therefore can rearrange that equation for our purposes, and we can say that Ek, the kinetic energy of the electron, is equal to h nu, that's the incident energy, minus the threshold energy. So we can also rearrange that a little bit more. So we also should know from general chemistry that we know that E is equal to h nu. We mentioned that already. But nu, the frequency, is equal to the speed of light divided by the wavelength. And I'm sure you've also heard Einstein's relativistic equation, relative mass and energy, that E is equal to mc squared. So combining these two, we have that hc over lambda is equal to mc squared. So if we cross the c out there, so we find that h over lambda is equal to mc. Now this is the mass times the velocity of the radiation. So this really is a momentum term. And that brings home to you the idea that energy can be regarded as a particle in nature, and the photons, if you like, have a certain momentum, and it's this momentum property of the photon that explains the photoelectric effect. So this was a really significant finding, because what we've known for some time, or physicists had known for some time, was that energy has a wave-like nature. You have phenomena like diffraction patterns, etc., and these can only be interpreted in terms of a wave-like nature. But in certain cases, we see, and the photoelectric effect is a really good example, it behaves like a particle. So this transformed, if you like, the whole interpretation of what we understand as energy. So energy can behave as a particle, or it can behave like a wave.